Hello class, in this video we're going to be looking at valence electrons and charges and kind of see the pattern that develops on the periodic table. This is going to help us in later units with bonding. So let's kind of take a look at these different trends on valence electrons and charges. So first let's review valence electrons. As we should know now, valence electrons are the outermost electrons, or the electrons on the highest energy level. And so I have two examples here that we can kind of go over in two different ways to look at it here. Also, if we look here at fluorine, this is the electron configuration. And just looking at the electron configuration, we can figure out how many valence electrons we have, because these are the electrons on the highest energy level. So if we're looking at the highest energy level we have here is 2. So anything with a big 2 in front, we want to count up those electrons. So there's 2 there, this is a big 2, and there's 5 there. So we have a total of 7 valence electrons. Or you can look at Bohr's model. We have 2 electrons on the first energy level, but that's not the outermost. The outermost is this energy level here, the second one, and we can just count them up. Starting here, that's 1, 2, 3, 4, 5, 6, 7. Either way, you get the same number of valence electrons. Let's look at another example. Here's magnesium. And with magnesium's highest energy level is 3. So we look at anything that has a big 3 in front of it. None of these, only this one has a big 3, and that's 2 valence electrons. So we have 2 valence electrons there. Or we can look at Bohr's model where we have 2 on the inner first energy level, we have 8 on the second energy level, and then we just have this 1 and 2 on the outermost energy level. So again, just the 2 valence electrons. So this process could get very tedious. Especially if you have to write out the electron configuration or draw a Bohr's model for every single element. Every time you wanted to know how many valence electrons there are, and we're going to need to know that very often. Luckily enough, there is a pattern that we see on the periodic table that allows us to predict the valence electrons of the majority of all of the elements on the periodic table. Alright, so let's take a look at our periodic table here. And let's see if we can't see where the pattern is. If we're looking at magnesium on the periodic table, here it is, we know that its highest energy level ended with the subshell S and with 2 electrons. And just by the pattern here, all of these, because this is the S block and this is all going to be S2, all these are going to end with S and 2. So they're all going to have 2 valence electrons, as we see here. So any of these here in this group, the alkaline earth metals, are going to have 2 valence electrons. If we look at fluorine on the periodic table, remember fluorine had S2 and then a P5. And actually everything in this group is all going to have some combination of this, whether it be 2s2, 2p5, 3s2, 3p5, and so forth. They're all going to have s2, p5, and if we add up those, we're going to end up with 7 valence electrons. So everything in the halogen group here is going to have 7 valence electrons. And we can see this pattern on the majority of the periodic table here, where this group, the first group, group 1, is going to have 1 valence electron. Second group, 2 valence electrons. We're going to skip the D block, and the reason why we skip this D block here is because the transitional metals have a variance of valence electrons. We can't really predict them as far as groups go. But if we end up here on the 13th group, the boron family has 3 valence electrons, carbon family 4 valence electrons, nitrogen 5, oxygen family 6, and then our noble gases with 8 valence electrons. So I highly recommend taking your periodic table out and writing the number of valence electrons on the top of each group that we have here. If it's in the S block or the P block, so anything in the S blocks, or S block or P block, we're going to be able to predict how many valence electrons they have just by looking at the number at the top of their group. So 2 for calcium. If I'm looking at chlorine, we got 7. So it's very easy if we just write this on our periodic table to do that. We don't have to write it the whole electron configuration, draw a Bohr's model, or anything like that. We could just have these actually labeled on our periodic table. So what you may see here also is that we have the charge listed above each group here. And you can see that some of them are positive, some of them are negative. We have a 0 charge here. And what I want to talk about now is, well, how do we know how to predict the charges for each group here? How can we say, okay, these group are going to make +3 ions, where this group is going to make -1 ions? How do we make that prediction? And it has something to do with the valence electrons. So let's look at this. So the driving force behind those charges is this octet rule, or the rule of 8, you'll hear me say. And that just states that atoms gain, lose, or share electrons until they are surrounded by 8 valence electrons. So they want to achieve the same number of electrons as the noble gas closest to them on the periodic table. They want this S2P6. And if we take a look at the periodic table and the noble gases here, we see that they don't have a charge because they had this fulfilled this octet rule, or the rule of 8, having 8 valence electrons. They're not going to have a charge. So how do the others get these charges? Why do some elements gain while others lose? And how does losing electrons get you to 8 electrons on your highest energy level? So we're going to look at a couple of examples. Okay, so we have our same examples here. We have fluorine and we have magnesium. We have the electron configurations here of both. And what we need to remember from the octet rule is that we want to have a configuration where the highest energy level has S2 and a P6. If we look at fluorine, we have 2S2, 2P5. That means it just needs to gain one more. If it could just make this 5 into a 6 just by gaining 1 electron, it'll fulfill that. So that's exactly what fluorine does, is it gains 1 electron. And since it's gained 1 electron, that means it has one more negative charge than it does positive charge, and it's going to have a -1 total charge. Remember, the protons are going to be 9, and now we have 10 electrons. That's going to give us a -1 charge. So what we see with nonmetals is that they are going to gain electrons, and when they gain electrons, they're going to form negative ions, and we call those anions. So that's what happens with nonmetals. But magnesium is a metal, so it's not going to do the same thing as the nonmetals like fluorine. So how's it going to get to an S2P6? Well, if we look here, we have 3S2 and we don't have a P. But if we look right before here, we have 2S2 and 2P6. So we have an S2 and we have a P6. The only thing is, we have this higher energy level, this 3S2. Well, if we lose that and no longer have that, then we're going to be left with our 2 electrons on the S and 6 on the P, giving us 8 valence electrons. So what happens for magnesium is that it's going to lose 2 electrons, and when it loses those 2 electrons, this is from the 3rd shell here, it's going to lose that entire shell, and now what we're left with here is 8 valence electrons, what it wants to satisfy the octet rule. So what happens then is that we have 2 less electrons than protons. We have 2 more protons. Protons are positively charged, so this is going to have a +2 charge. And so what we see in metals is that they are going to lose electrons to get to 8 valence electrons. They're going to form positive ions, and those positive ions are called cations. This gives a lot of students trouble because we're losing electrons, and that becomes positive. just remember the electrons are negative, so you're losing negatives. That's going to make you more positive. The nonmetals are going to be gaining electrons, and that's going to be more negative. Another way to look at it is, instead of losing it, you're giving away electrons, and that's something positive, so it's going to give you a positive charge. Instead of gaining electrons, you're really stealing the electrons, and that's going to give you a negative charge. So that's just another way to kind of look at it, maybe help you remember it. So let's take a look at this on our periodic table and try to look at the trend or the pattern on the periodic table to help us predict this, so we don't have to go through this whole method over and over again. So here we are again at our periodic table, and if we look at fluorine and fluorine's family, the halogens, all of these, remember, have 7 valence electrons, so they all need 1 to get to 8. So each one of these will gain 1 electron. And if you're gaining electrons or stealing electrons, that's negative, and you're going to have a -1 charge. If we look at magnesium and magnesium's family, the alkaline earth metals, they all have 2 valence electrons. And remember, the metals, they give them away. So they're going to lose 2 electrons, and since giving is positive, they're going to have a positive charge of 2. And this pattern repeats itself throughout the main group. If we look at the alkaline metals, they have 1 valence electrons. They'll lose their 1 valence electron and have a +1 charge to get to 8. The boron family here has 3 valence electrons. They will lose 3 valence electrons to get to 8 valence electrons. And oxygen's group here has 6, just needs 2. It'll steal 2, giving it a -2 charge, getting to 8. And so now we can predict the majority of the charges of the elements that we have here. If we're looking at phosphorus, we just go up and say, oh, okay, that's going to be a -3. This is going to be very, very useful for us when we're looking at bonding. That's going to be in the next unit. So if you do have any questions, please bring them to class, and we will discuss this more then. Thank you.